Alright, so we have this beautiful quad rotating in 3D space, projected correctly, not depending on the screen size. Very good. Let's implement a very simple camera to move around. We will use Linux library functions for that because they are very nice. And let's think, what do we need to implement movement? We need some kind of camera structure, right? That would have a position of vector 3 in space. By the way, I do have vector 3, but they are defined here locally in this init function. Let's just move it closer to our other linear algebra type definitions. So it needs a position and probably a target to look at, because that's pretty easy way to deal with stuff. So you have a position and the target to look at, and then you could have a really nice function in Linux called Linux look at, which would say, yeah, of course it's not matrix 3 but matrix 4. I won't make that mistake again. Which will give us a view matrix, so V from the eye position, which would be of course our camera position, to the center of whatever we want to look at, and that would be our target position, so G camera target. And then it also needs an up vector, which is just up to the positive Y. And we don't want to change the flip z axis argument because it needs to be consistent. And yeah, that needs to be a vector 3, or we could actually say we want exactly the F32 version like we did here, just to be consistent. Then it will infer the type of these numbers to be F32. So now we actually want to multiply to insert our V here. So we first translate whatever vertices we draw by model translation matrix, then we translate them by the view translation matrix, and finally we project them with the projection matrix of the perspective. So now let's initialize this to something sensible. So let's actually not move our object, so let's not just translate it at all. We could also just remove this, but let's leave it for now. Instead, let's translate the camera. So when we initialize the application here, we can just set up our camera to be something like a position should be, let's say, a little bit to the back, like 2 meters back, and the target at which it looks would be 0, 0, 1. So it would look 1 meter forward, so like to the minus z. And this should already give us the same effect. So we are now looking at the same quad, except that the quad actually states as the 0 coordinates, and the camera is staying a little bit back and just looking at it. And now let's just implement some control for that. So for that, we actually finally need to handle some events from Sokol app module, and namely we want to do a partial switch on the event type, and the event types we are interested in are mouse move, because we want to control our look with the move, then key down and key up. So what do we do with those? So for the mouse move, what we want to do is accumulate whatever movement happens between frames and store it, so we can actually use it in the frame to calculate, or rather to update our camera. So let's just have a global variable, mouse move, like this, of vector 2 actually, because of course it's two-dimensional. So what we want is to just accumulate this like this with the vector of delta x and if mouse delta y, which is handy, it's already float 32. And then at the end of the frame we actually want to clear this, so this value is just per one frame. And now we can actually do some logging to see if that works. So log debug, mouse move, you see it shows some values, very nice. And if we stop moving the mouse at 0. And by the way, the reason I don't really put this to the global structure and instead leave it as a normal global variable is that even if we even if we consider the hot reloading, this mouse move is something that happens really per one frame, and we don't really want to store it in a shared game memory and restore when we reload the game DLL, so that just doesn't really make sense. So this is fine to be a proper global variable. Now for the key down and key up, because Sokol doesn't really have something like array_lib is key down or something, it only provides us with these two events, so we need to handle this ourselves. So what we can do is have another global variable called key down, and this one would be a fixed array of application key codes, and we just use bools for that. Now Odin will complain now that the array is non-contiguous because the number of elements in the enum is actually different from the maximum value of the enum, so it's basically a sparse mapping, but we still want to use a fixed array for that. So what we can do is do as it suggests and use the sparse directive here. So now the only thing that we want to have here is on key down, we just say key code equals true, so we set this one to true and now to the false. So now this variable will always contain our key, the state of whether some key is pressed or not. And just like with a mouse move, I think it's fine to be reset if we reload the DLL, so we don't really care about this. So alright, let's maybe log debug, key down, space for example. So you see it's false, I press the space, it's true, I release the space, it's false again. And this is something that we can use to control our camera. So now let's just have a function update camera or something and pass the delta time to it because we need that for the movement. And let's create this function. The camera is a procedure. I need to learn to call these procedures because it's a procedural language, not a functional language, right? Anyway, F32, and here we want to update our camera. We want namely to update the position and target. So first, the position, that is very easy for now. What we want to do is get the move input from our keyboard. So we say move input, that would be just a vector 2. So X would be to the side, right? And Y to be forward and back. Now we say if key down W, then do move input Y 1, right? So otherwise, if key down S, move input y should be -1, so we want to move back. Now we want to do the same for the side move, for the strafing. So A and D, and that would be move input X for -1 to the left and X with 1 to the right. So here we have a move input. Alright, now we maybe want to have something called move speed. So how fast do we want to move? Let's say 3 meters per second. And we want to move forward. So what we need to do is to compute a movement direction. So move dir should be a combination of forward and actually forward multiplied by move input y, so it's either 0 or forward or backwards, so minus forward, plus right multiplied by move input x, right? So this would be our movement direction vector, and we need to define forward. For now, let's say forward is just always forward in our coordinate system, so -z, and back, right is of course just positive x. So we have this nice vector 3, so nice vectors that are corresponding to our coordinate system. And now we calculate the movement direction with the input, and now we can say our motion that we want to apply would be a RenderDoc normalized vector. I hope you guys all know what is that. So it will just ensure that the movement vector is of a length of 1, because if we say move input y and move input x is, for example, 1, then the length of this vector will be more than 1. So the diagonal movement will be more than we want. That's why we want to normalize. They want to always normalize this vector. And by the way, we just want to not just normalize, because normalizing a 0 vector, in case we don't have any movement, will return as in a weird value of not a number components in the vector. So RenderDoc provides another handy function called normalize 0, which will always return a proper normalized vector, right? So it would just return a 0 vector for movement direction, which is well, for the motion, which is totally fine in this case. So we want to have our movement direction, then finally multiply this by the move speed and multiply this by the delta time. So the motion represents how much did we move this frame in which direction. And this is something that we can easily just add to our camera. And now if we run, and I can press, and we can actually already move. This looks kind of weird, so let's figure it out. When I strafe, it looks weird. That might have to do with the rotation. That is just making me a little bit... Oh my god, what the hell is going on? This is not right. So let's debug. Let's maybe just print our camera position to figure out what's going on. We'll debug camera position and maybe also the motion to see. So when I'm moving forward and backwards, everything is fine. When I'm moving left and right, the movement becomes kind of strange. Ah no, actually, it's not a problem. The problem is that we are moving, we're changing the camera position, but the camera target is the same, so we are still looking at the same point. And for now, let's just say that we want to update the target, so we look always at the camera position, point plus forward. Plus forward. I'm sorry, I'm already getting a little bit tired, so maybe I should wrap up this video, but I just wanted to get it working. So now we can at least move, but not really move directionally or change how we look. So this is what we should be doing next. Yeah, this works pretty well. So now for the look, what we want to have is, of course, some number to control the sensitivity. So that would be look sensitivity, which would be something like 1 for now. Of course, we should use the proper syntax for constants. And we need to collect the look input. So look input of vector 2, that should be just mouse move, basically, multiplied by look sensitivity. So this is one thing to have. And we also need to store this like accumulated. So when we change the look, because we only have the position and the target for the camera, and this is something that we are supposed to calculate from the look vector. We need to store it so we can add our input to it. So let's do exactly this. Maybe we should store it in the camera. That would be a vector 2 of look, and it's fine to have it 0 by default. And what we will do here is, of course, just say g camera look plus look input, log debug g camera look. So now I'm moving the mouse and this value is changing. What we want to do probably is to keep the values in some good range. So for example, for X value, which is our yaw rotation, it should be clamped, or rather wrapped, by 360 degrees, right? Because we are considering this deltas of the mouse are deltas in the degrees. So thankfully the core math library contains a nice function called wrap. So we would say we want to wrap this value by 360, so it never exceeds this range. So now no matter how much I move the mouse, it will be within this range, which is kind of nice. And by the way, one other thing is that for the first person controls, or like for any kind of immersive controls, we want to lock the mouse and hide the mouse cursor. So let's do exactly that in our initialization function just after the SG setup. So if we could initialize the graphics, what we actually want to call is Sokol app show mouse false, so we don't want to show the mouse cursor, and as app lock mouse, so we want to prevent it from going out of the window. So we want to not show the mouse and we want to lock the mouse, and this is how we do this. Now if we run, you see no mouse cursor and it's not going out of the window. And actually now closing the app is a little bit annoying because we need to alt tab to make this work. So this is not really nice. So let's maybe handle that. Maybe let's have something like should quit boolean or something. And maybe when we actually have a key down, like when we are handling in the very beginning of our frame, we say if escape key is down, then just say should quit equals 2. Actually, we don't really want to have it as a one-liner, because what we want to do here is set this variable to true, and then just return, so we don't execute all this. And come to think about this, we don't really need the should quit here at all. I mean, we could maybe use it to call this from other places, but if we want to just handle this escape thing here, we can just say sapp.quit directly. So this will just call the cleanup function and exit the application. So now I can run, press escape, and it works. Anyway, back to the camera updating. So now we have this look, the X is wrapped, and the Y is something that we want to wrap around. I'm sorry, not wrap around, of course. We want to clamp it to some values. And the quite common values is to clamp this value from -90 to 90, so we can only look to the up and to the down and not more. So now we have these values, very nice, they are clamped. So this will be our look degrees, so yaw and pitch. And finally, what we need to do is calculate these guys based from our look. And thankfully, linalc can do this very easily. We can just say, you know, give us a look transformation matrix, linalc mat4 yaw pitch roll. So the yaw should be linalc 2 radians. Let's not forget about this. By the way, maybe if we use this function a lot and we don't really want to always prefix this like this, what we can do is just say 2 radians is linalc 2 radians, like a constant, basically. Very handy. So we can just now say just 2 radians, and that would be look. So what is this? This is yaw. So yaw is X, and the pitch is look input Y, and the roll is something that we don't really use, so this is 0. This complains about can't assign 2 radians of type T to, oh my god, really? Why? Because look is a weird undeclared variable, of course. I'm sorry, it's getting late. And here I also wrote some weird shit like look input. So of course we want to use the camera look for that. And now we can just multiply our forward and right vectors by this matrix. And now it complains about something else, because the look mat is matrix 4, and this needs to be a vector 4, right? So we want to multiply 4x4 matrix with 4 vectors, and as I said, the just like in GLSL, the fourth coordinates, the fourth component should be in just 1, but ultimately, actually, we don't have the vec4 defined, so this is what we can do very easily here. And now we still want to have 3 component vectors for all the other stuff. So what we can do, this is another cool Odin feature, which is also present in GLSL, but in other languages it's not really there, that we can just do this, give us a vector 3 of x, y, and z components of this vector 4. This is really cool. I believe Unity Mathematics Library emulates this by generating some code, which is really handy as well. But having this as part of the language is really cool as well, because it doesn't really depend on any specific types. It works for all the fixed array types. So now we can actually look around. Yeah, the controls are a little bit weird. I believe we need to invert the mouse movement, so X and Y should be flipped, and the sensitivity is a bit too much. Maybe 0.3 is better. Yeah, now I can control it. So now, if I stop the rotation of this one, we can actually move around, And yeah, look at this cute wall. So that's cool, right? We can even draw multiple walls like this. So let's see what we need to do for that. So we apply the pipeline. The pipeline for the second wall will be exactly the same. The vertex buffer will be also exactly the same. The uniforms, this is all not exactly the same, because what we want to change is this thing, right? Because we want to pass different coordinates, different translation coordinates, and maybe even different rotation coordinates, values to it. So let's have a little bit of a object structure, maybe something like objects that should be a, yeah, maybe let's just have a name type like object. That would be a structure of, I don't know, translation of, or maybe just position, just pose of vector 3, right? Rotation of vector 3, so we will use yaw, pitch, and roll, because it's very easy to understand. And yeah, that's it for now. So let's have a bunch of these objects. Let's have one at 0, 0, 0 with actually no rotation at all, right? And now what we want to have is do this stuff in a loop. So for object and objects, we want to do this draw call passes, but what we want to do is construct new vs params. So what we can do is just copy this out, copy this in, cut this out, and we already calculated the perspective projection, we already calculated the view projection, the view matrix, and what we need to do is to calculate the model matrix, and we need to do this from obj position and obj rotation x for yaw. Is it x for yaw? No, that should be, I think, y for yaw, because we are rotating around y-axis. Obj rot, so this would be pitch, this is actually x, because we are rotating around the x-axis, and rotating around z-axis would be our roll. So hopefully this will still work just fine, but now we can actually draw multiple objects of the same type, you know, so we can just move 1 meter to the right and draw exactly at the same wall to be like this. They are separated because, well, the size of them is actually 60 centimeters, so maybe, just maybe, make it a proper 1 meter. So now they are perfectly tallying to each other, and we can actually build some kind of level like that, right? We can say, yeah, let's have another one here, and then maybe we would have another set, like maybe 2 meters to the back. So now we have this small corridor. We can also have a floor, right? Like, let's say we have at 0, but we want to what we want to do is rotate them by 90 degrees around x axis. So here they are, and here we see actually some bug which is interesting, which has to do with the depth testing, of course. And the other one is that we are using the degrees instead of the radians again. So what we need to do is, of course, 2 radians. As I showed before, there are a lot of other useful functions to create those matrices, like the one to create one from quaternion, which is much better for rotation than this axis, especially for like dynamic ones. But we are gonna keeping things very simple. So now we have it pretty much positioned almost correctly. It should be positioned, I believe, a little bit to the back and a little bit to the down, to the bottom, right? And we also want to have probably a little bit more of those 1 meter to the back to have our corridor complete. So now the problem is that drawing, actually what we draw last, always overdraw what we drew first, and that has to do with depth testing. This is part of the configuration pipeline. So what we need to do here is, of course, to configure our pipeline, and this is the field that controls that. So we say depth, and we need some configuration here. We don't really care a lot about them. What we want to have is that every draw that we do writes to the depth buffer, and then when it decides whether we want to actually write and to draw a pixel, we compare it about with the current value, and we only draw when our value is less equal, I believe it's called, than the one that was written before us. So if the object is more in front, we draw. If the object is in the back and obscured by something else, we don't really draw. So that should fix the issue, and that's nice. You see, that's very good, very nice corridor. We can of course fly around with our camera. What we can also do is maybe have yet another texture. So we have this whole pack of textures. We have the walls, right? Maybe we can use some nice floor, or maybe even some grass. I don't know. Let's use the tiles. They are pretty beautiful. I would like to make a game maybe out of this someday. Anyway, so what we can do is to, of course, load this thingy. And how we do load, if you remember, it's in the initialization. We have this function to load stuff and to make an image. Maybe we should extract it in a separate procedure. I'm sorry, not a function. So load image procedure, and it needs this. It should return the SG image because it actually uploads it, and maybe we should even call it upload, but I don't know. And this is not G image, but a local variable of image that after successful upload we will just return. So what does it need is a file name, which is a C string, or rather file name, which is a C string. So like your normal null terminated string, which is what STBI load expects. And now here with a G image, I can just say load image of whatever we had before, this brick. So this works. We can also load the other one. So maybe we can use image2 and load it here as well. And of course, loading and unloading is part of the whole resource management in your engine. So this is something that you will have to design for the whole structure. I'm just showing how to do the Sokol, oh, I'm sorry, how to use Sokol graphics and Sokol app in Odin. So yeah, now we have two textures in our video memory. And what we could do is actually to specify it here, like which image to use. So for the walls, we can say that, oh my god, for the walls, yeah, I'm pretty bad at multi-cursors, but anyway, for the walls we want to say the first image, right? And for the floor we want to use the second image. And what we need to do now is to actually also change the bindings every time we change the image. We won't really track the image right now because that's a whole different topic, but we want to, what we will do is create a binding object, binding of course SG. Actually we can do this like this, SG pipeline. So no, it's not a pipeline, I'm sorry, it's bindings, SG bindings. And for every object we would say B is bindings, and we want to, in this local copy, we want to modify the images, images, so img text should come from the object image, right? And now you see we have a pretty nice corridor. So yeah, so of course this is very not super optimal, because like right now we are not really looking at anything, like we only see like one polygon of this wall, but actually everything else is being drawn because we explicitly say please draw us, please draw the objects, and we can actually launch this nice tool called RenderDoc that allows you to inspect what is going on with your rendering pipeline. So if we say C code hello Sokol, so this is what we just compiled, and run the game, it will it will run it in a special mode that is gonna do some capturing. And if we press F12, it will capture the whole rendering of the current frame, and we can see all the operations that were done here in order. So this is all our draw calls, so we have like this number of draw calls, and if we actually do it a bit differently, so what I want to show with this is that we actually do all the draw calls because we don't do any culling. We should do probably something called frustum culling or some more sophisticated algorithm. This is a whole science behind it. But let's launch the game again through the debugger, through the RenderDoc, so the doctor, right? And then just capture yet another frame and see how it's actually being rendered. So we have the clearing with the default gray color, and then we draw it one by one exactly like we specified in our code. And in this tool we can actually see what the meshes are we using. So this would be our mesh, which is just a quote. We can specify that we are using the right-handed y-up, so the forward z is minus. Yeah, we can take a look which resources are we using. So we have like two textures here, for example, like this is one of it, and there is another one like this one, right? And all the buffers like index buffers and vertex buffer. I believe this one is a vertex buffer. Yes, you see the usage is a vertex buffer. We can actually take a look at it, and what is cool about this, that we can actually specify, okay, this vertex buffer is of the structure of what do we have, position, which is float 3. No, yeah, I believe it's C style, C syntax, right? So float 3 position, then we have float 2 of UV and float 4 of color. Is it our vertex data structure? I don't remember already. I believe so, right? So position, color, and then UV. So if you do it like this here as well, and then apply, and yeah, it needs, I guess, the name like vertex, and then apply, we can actually see it as a table with all the data correctly parsed. This is really nice to actually see if there are some really weird problems in your application. And we can of course do for the other buffer, which is our index buffer, which is u unsigned int 16th, which is u short. So this is our indices that we specified. And there's a lot of stuff here. This is a really great tool for debugging rendering, so check it out. Alright, I think we can finish at this. You probably have a nice idea how to use Sokol graphics with Odin. So thanks for your attention and goodbye.